Everyone, and welcome back to the Fluctus channel. Contrary to popular belief, jet engines were actually invented as early as the 1920s. However, they did not see widespread adoption of aircraft until the mid-century. These jets, also known as air-breathing engines, work by discharging a fast-moving jet of heated gas, often relying on internal combustion to increase propulsion. For years, manufacturers like Francis Safran embraced several methods to build their jet engines. Throughout the 1980s, the company relied heavily on traditional machining techniques as well as newer computer-controlled processes. From lathes and million-dollar machines to special measuring and cutting tools, the design and assembly process was heavily human-dependent, despite the very low margins for error. Though most jet engines have thousands of moving parts, how they work is actually quite simple. The open front of the engine allows it to take in air from the atmosphere and compress it. At this point, fuel is added, ignited, and expelled out the back to produce thrust. The compression is accomplished via a series of fan blades, which increase the air's pressure and temperature. That temperature only increases when the fuel is added and ignited in the combustion stage. By the time the superheated air reaches the nozzle, it is capable of producing thousands of pounds of thrust. Though jet engines have remained more or less the same over the years, new technology has allowed for dramatic increases in power and refinements in the design and manufacturing process. Most engines are now constructed, repaired, and revitalized in massive facilities known as megafactories. Both military and civilian agencies operate megafactories all around the world. Some, like Tinker Air Force Base in Oklahoma, United States, cover areas as large as 5,000 acres. Tinker is home to the Oklahoma City Air Logistics Complex, responsible for providing maintenance, repair, and overhaul services for various military aircraft, including the KC-135 Stratotanker and the E-3 Sentry AWACS. On the civilian side, GE Aviation has multiple facilities and factories spread out around the world. Many factories use state-of-the-art design and production techniques to produce engines for popular civilian aircraft, like the Boeing 747-8 and Boeing 787-9 Dreamliner. GE is far from the only company manufacturing jet engines and jet engine parts. In fact, as technology improves, the industry has only become more and more competitive. CFM International is a Franco-American venture between GE and Safran that produces turbofan engines for roughly 39% of the world's commercial planes. The organization's SNECMA Pulse, like at Villaroche, France, is largely considered one of the most advanced turbine assembly lines in the world. This massive facility utilizes a 5-step assembly line to complete engines in just 2.5 days. American company Lockheed Martin does the same while remaining largely focused on military aircraft. For instance, Lockheed is the company behind the F-35 Lightning, the most advanced fighter jet on the planet. The B variant of this aircraft features an upward-facing engine behind the cockpit that allows for vertical takeoffs and landings. The aircraft also features a single Pratt & Whitney F135 PW100 afterburning turbofan in the rear, which is capable of producing up to 43,000 pounds of thrust. Pratt & Whitney is largely recognized as one of the top aerospace manufacturers in the world, alongside General Electric and Rolls-Royce. Though based in England, Rolls-Royce has designed and manufactured engines and other machinery for dozens of countries. Its Trent XWB engine is referred to as the most efficient aerospace engine yet developed. This high-bypass turbofan is assembled in several stages at the Rolls-Royce assembly plant in Dahlewitz, Germany. The Trent XWB consists of more than 20,000 components. The compressor has 8 stages in all, and the fan boasts a diameter of nearly 10 feet. In 2006, the engine was selected to power the Airbus 350, and it continues to prove itself both in the field and factory-based testing. The Dahlewitz facility is so advanced that it takes just a handful of assembly technicians to assemble a completed Trent XWB. Given the sheer number of parts and components that go into making a modern jet engine, manufacturers like Pratt & Whitney have developed a wide range of approaches to control the sourcing and assembly process. In Pratt & Whitney's production readiness room, the team tracks the movement of thousands of parts to identify potential issues before they arise. Indeed, though Pratt & Whitney makes the engines, dozens of third-party companies are often required to produce the various parts. If one of these components is lost, late, or damaged, it can drastically affect the overall operation. From gear systems to bolts, the command center tracks the movement and availability of more than 45,000 parts daily. This allows the company to predict potential delivery problems as far ahead as possible, mitigating any shortages and allowing Pratt & Whitney to meet its contractual demands. Of course, even the most detailed assembly process must be followed up with extensive testing. For the Pratt & Whitney F135, tests like these are critical steps in developing and certifying each product. Without them, the company could never guarantee the Air Force a safe and reliable operation. During testing, the engine is subjected to various conditions and scenarios, including simulated flight conditions and extreme temperatures, pressures, and forces. Such evaluations are also critical to providing upgrades to the F-35's engine system. Since technology moves so fast, it's critical that the product line be able to meet the ever-changing requirements set forth by the U.S. military. The most notable of these include increased range, better fuel burn, and improved thrust. Whenever a jet engine is constructed, serviced, or upgraded, the next step is typically a specialized facility known as a hush house. This is an enclosed test cell designed to capture and reduce the noise generated by aircraft engines during evaluation. During the test, the engine is operated at various power settings, while its performance and noise levels are monitored and measured. The value of the hush house test is that it provides a controlled environment where the engine's performance and noise characteristics can be studied without causing excessive noise pollution to the surrounding areas. It also allows engine manufacturers and aviation regulators to verify that engines meet performance and noise requirements before they are put into service. Rolls-Royce embraced an advanced battery of tests after its F-130 engines were chosen for the B-52 Stratofortress upgrade program. Many of these tests took place at the NASA Stennis Space Center in Mississippi and included crosswind performance evaluations and electronic control experiments. These tests represented the first time a pod of two F-130s was tested side by side. Not only are these new engines designed for maximum fuel efficiency, but they are durable enough to remain on the B-52 throughout its nearly 100-year service life. Aside from producing high-quality, high-efficiency jet engines, Rolls-Royce is also leading the charge on the transition to hybrid and electric aircraft propulsions. In recent years, the company has announced its mission to transition to all-electric aircraft engines as part of its effort to reduce carbon emissions and to contribute to a more sustainable aviation industry. Their vision is to develop and commercialize the world's first all-electric aircraft engine for regional passenger flights by 2029. Rolls-Royce is also working on hybrid electric engines for larger commercial aircraft, which it plans to introduce by 2035. In order to achieve this mission, Rolls-Royce is investing heavily in research and development with a focus on electric propulsion systems, energy storage, and power electronics. The company has also formed partnerships with other leading aviation firms to develop and test new technologies and prototypes. Since 2020, Rolls-Royce has been testing the Accel, an all-electric demonstrator plane that has since become the fastest electric plane in the world. Nicknamed the Spirit of Innovation, the Accel represents the first step toward a more sustainable aviation future.